So welcome to the 13th class of data analytics. Today is quite a special session because I'm going to be covering the last chapter of the book, which is dedicated to graph data. Okay, so let me first say there are three words you should remember that everything you deal with in life, right? When you create an abstract representation, it always comes down to very few things. So the first word you need to know is entity. That means whatever is a thing you're working on. Okay, so entity could be a particular data point or whatever, right? But it could be the subject of your study. So that's entity. Okay, associated with each entity is a set of attributes. Okay, so attributes are like adjective. Okay, so entities define the index, so to speak. Okay, whereas attributes defines the vector value. Okay, so if an entity, if a Basai student, right, and my information vector consists of well, student ID, grade, concentration, let's say. Okay, those are the attribute. Okay, those are the attribute of you as a vector. So you got entity. Each entity is associated with a set of attributes. But what if the attributes themselves are other entities? In which case, we will call this thing relationship. Okay, so if entity is I, and the relationship is I is a friend of J, okay, then that attribute, okay, so knowing J is an attribute of I. Knowing J is an attribute of I. However, it's not an attribute that can be defined by I alone, right? So in a way, it is an attribute of the item I that requires indexing J. Does that make sense? This is why we are going to see that when we go to relationship, at minimum, there's always two index, I and J. Okay. So again, there are, let's say there are 10 of you. That's I from 1 to 10, right? But if you are a good friend, well, hopefully you're a good friend with yourself. So maybe there's a connection, relationship between I and I, that's you and you, right? And there's also a relationship between I and J, so somebody else who's not you. Okay, so we're talking about entity. Associated with each entity is a set of attributes. But if the attributes themselves refer to relationship with other entities, then we call that attribute relationship. So I'm just going to say it right now that everything you have an abstract representation of in your head is going to come down to one of the three things. You're talking about entities, you're talking about attributes, you're talking about relationships. Okay. Now, most of the time, up to now, we talk about data. We usually think of tabular data. And if you think of an Excel, you're going down to the row. That's the I, right? That's the indexing of the attribute, right? When you go to the column, the measurement, the grades, the height, the weight, the whatever, that's your attributes, right? But if instead of going down to I and pointing down to attribute J, it's about which I knows what to what other I. In other words, which I knows J, then it's about relationship. That's what today we're talking about. Okay, and so I do that a little bit. Now I have here is quite interesting. It's a little bit of my personal history. This was my proposal back in 2004. So that's kind of nice because this is literally 20 years ago when I drafted this. Okay, this was when I was working for the Bank of Thailand. Use an eigenvector to quantify relative systemic importance for risk-based banking supervision. Now, you don't need to know anything about banking supervision. You know banks, right? Banks are a very important part of a modern economy. And banks are not like any kind of companies where, you know, if it go bankrupt, it's not a big deal because banks take money from people, ordinary deposits. So if they go bankrupt, you might lose your money, right? Okay. So you don't want banks to go bankrupt very often. Even though you have something like depositor insurance, it's not going to cover everything. Anyway, it's going to be highly disruptive if banks fall. So Bank of Thailand is looking after the health. It's like making sure that commercial banks don't take advantage, don't make so much profit taking advantage of the people, but at the same time, they also don't make so much loss that they can't stay afloat, right? So think about it. If I look at individual banks, let's say there are 20 banks in Thailand, let's say 10 banks, important banks. How would you say among the 10 banks, which one is important? Well, put your marketing hat on. What would you say? You say it's a market share, right? Okay, so maybe it's market share. Maybe it's the size of the balance sheet. Those are what? Those are attributes. In other words, if I look at one bank, I can look at that bank's balance sheet and I come up with a number, right? And that number is indexed to bank I. So I could be Siam Commercial Bank. Okay. J could be Krung Thai Bank. Okay. So the number that has to do with the balance sheet of each bank is individual, right? Therefore, those are attributes. But what if there's a number that says, I don't know if you know this, but you can borrow from bank, but banks also borrow from each other. Okay. So if banks borrow from each other, not because they don't have enough money, but because they need liquidity. Okay. So they have money in the form of liquidity and they have money in the form of non-liquid asset. But anyway, at the end of the day, to balance their liquidity requirement, I say, oh, I'm a little bit short on cash on hand. Okay, it's not that they're not out of money, but they want they're a little bit short on cash. They can borrow from other banks, and this happens all the time. It's not a big deal. Okay, it's part of daily life. It's called liquidity borrowing overnight. So on a particular day, if I want to look up what Siam Commercial Bank owes or borrows from Krung Thai Bank, that number, would I call that attribute number? In this context, I would call it relationship number because that number has two indices, right? Siam Commercial Bank borrows overnight amount, however million, okay, from Krung Thai Bank. So I borrows from J, right? Now, tomorrow it could be the opposite. Tomorrow, Krung Thai Bank is a little bit low on cash reserve, borrow from SCB, right? In which case, it is the JI, right? So amount IJ and amount JI are different, right? Okay. So that's the sort of thing we want to get into. Now, I want to show you this is because it's kind of funny. I'll come back to this later. But the way I want to analyze relationship between banks, I cite an example of what's called, you guys watch football, right? In English football, let's say you want to see that which bank, sorry, not which bank, which football team is the strongest team, right? So what do? You look at total points at the end of the season. Does that make sense? Right? So in fact, that's how Premier League table works, right? By score at the end of the season. Okay. Now those number, okay, is that attribute or relationship? It's attribute, right? This football team has racked up so many points over the season, and if it's got more points than anybody else, then that team wins a championships league for that year, right? That league's a championship for the year. Okay. Now, what if I want to be a little bit more detailed? I say, well, you know, it's fine. You get all this win, but if a strong team, okay, let's say the top team beats another top team, gets 3 points. Okay. If that top team beats like really low ranking, you know, on the verge of a relegation zone, does he get less point? Does that team get less point? No, still get 3 points, right? So what if I'm more interested in how did they get those points? So I'm not going to look at the points, total points earned, which is, you know, indexed by team. So Arsenal has got one number, Chelsea has one number, Man U has one number. But now I want to look at the quality of their games. So of all the wins, did they beat strong opponent? Or did they get a lot of 3 points by, you know, beating really weak opponent, right? In which case, are those numbers, strictly speaking, in my, you know, definition I gave earlier, is it attribute number? No, it's relationship number, right? For example, how many times has Arsenal beaten Chelsea? Okay, that number is not an Arsenal number. It's a number that indexes Arsenal, comma, Chelsea. How many times has Chelsea beaten Arsenal? It's another number. It is number that has 2 indices, right? Okay. Well, I'll come back to this. I just want to show you that this idea of banks borrowing from banks, in a way, and the idea of football team beating one another has that kind of information. Okay, and in fact, it has similar kind of structure. And by applying abstract thinking, I was able to conceive relationship among banks, strength of bank and so forth, in a way that you would see in a British English football Premier League. Okay, but I'll come back. It may not make that much sense now, but remember this word called eigenvector. Okay, remember that word. I'll come back to it. Okay, so let's start today's lecture. Okay, so for that, let me go to the textbook, right? So open your textbook and also start your Mathematica notebook. Okay, so courses, now we are here. Okay, right, so now we got, where's my notebook? Can you see the notebook? Oops, sorry. You should turn. How come I can't see the notebook? Where's my notebook? What did I do my notebook? Okay, let's go to the. There it is. Okay. Data analytics. Okay, so notebook, start it up. Okay. Sorry about that. Okay. Right. So that's my prologue. Okay. Now, so this is chapter 1. No, we don't need that. Chapter 2, we don't need that. Shrink that. Chapter 3, we don't need that. Chapter 4, we don't need that. Chapter 5, we don't need that. Chapter 6, we don't need that. Now, chapter 7. Okay. So I'll try to follow this so I don't have to go back and forth, even though some of this, you know, I normally prefer to write on the board. Okay. So keep that in mind, okay, that we want to work with information that links or relate to entities. Okay, so it's not an attribute that pertains to one entity, but it's some quantity or some relationship, some variable that links two entities. And in the back of your mind, you just think anytime you need two indices, right? Anytime you think you need two indices. Okay, so now let's start, you know, as if we were a mathematician. They will start with definition. So this looks a little bit abstract, but you will see that, using abstract thinking, it's more general. So first of all, I'm just going to say it right out. I'm interested in this thing called graph. Okay, graph. Okay, the name of it, analytics on graph data. Okay, so before we get to the data part, you have to understand what I mean by graph. Okay, graph as a mathematical representation of network. Okay, this is very important. Graph as a representation of network. Network, by its very definition, well, think of friendship network, social network, right? Network is who knows whom. Okay, so in other words, you cannot have network information unless it pertains to two human beings, right? Who is one person, knows whom is another person. So there you go. There's IJ, right? IJ. Okay. So graph is a tuplet, meaning to define a graph big G. So this is kind of, let's make it really big. Big G here is a tuple. It requires two definitions. To define a graph, I need to define two things. I need to define big V and big E. Big V and big E. And you can memorize this because this is going to be like a standard notation. Just like when you go to statistics, they talk about random variable. It's always X. They don't start with P unless it's some special name, right? So this is a very generic name. G is the graph. Is two collection. It's defined by two collection. The first collection is called V. Big V is a collection of little v. Okay? Little v are what's called vertices. Vertices. Okay? Now, there's another word called nodes. Okay? There's another word called nodes. So, let me well, I'll come back. Right now, you don't have a picture. So, nodes. What do the nodes of vertex correspond to? You can think of it as a place where entities sit. Okay? Place where entities sit. So, because it's entity, how many index do you need? 1, right? So right now, there are actually 10 chairs for you, 10 people to sit. Correct? Okay. So the vertex, the vertices or vertex, plural of that, a vertices or node is where you would locate the entity, right? Now, up to today, whenever we talk about entity, we care about the attributes. Today, we're not going to care. Okay? So you sit on your vertex. I don't care now how tall you are. I don't care what grade you have. I don't care about your individual attributes. Okay? You mean nothing to me individually. Okay? Today. So you just V1, V2, V3, 4, 5, 6, 7, 8, 9, 10. So there it is. It's a set of vertices from 1 to n. Now, normally n is greater than 2, right? Okay. It's corresponding to the entities. Okay. Now, the big E is a set of edges. Okay. Another word for edges is called arcs. Now, they pair it this way. If you use vertex, you should use edge. If you use node, you should use arc. They just happen to be like historical custom, I guess. Okay. So whenever you see a paper that talks about individual entities as nodes, you will see that they use the word arcs. Mathematically, we tend to use V and E, hence V and E. Okay. Now, E is what the focus of today. E is the edges. The purpose of E is to connect vertices. So right away, E, you can see, has got 2 indices. Okay, has got 2 indices. Okay. So let me ask a very simple question. In a system where you have n vertices, how many edges can you have? Maximum number of edges. Well, it's n squared, right? Because you can have 10i. For each I, you can have 10 j's, including itself, right? So how many edges can you have? How many vertices? How many edges or arcs can you have? You can have n squared, right? Counting the one that catch yourself. Okay. Now, this is not yet general, okay, but we'll stick with this because if you think about it, this relationship, you can have more than one kind of relationship, right? Okay, so imagine from the same 10 people right now, 10 people right now, I ask about relationship of who is a friend of whom. Okay, then that would be one relationship. What if another relationship is who is the same project group, right? That's something else, right? And if you have 10 class, maybe in this class, you are in the same group as this person, the other class you're not, right? So in fact, it's not just that 100, it's 100 per relationship type, okay? But let's not get ahead of ourselves. Right now, I'm just gonna talk about one relationship type. Okay, one relationship type. Okay, so there it is, IJ. This corresponds not to the entities themselves. Again, we don't care about who you are as a person, how much you weigh, what is your grade. It's about who are you linked to. So it's IJ. It is the pairwise connectivity. Okay, so that's it. That's it. This is how you see the world. Entities with attributes. Today, we're not going to care about attribute. We're going to care about relationship between entities. Now, just now, I happen to mention group project. Some of you may think, hey, wait a minute. Group project is not a pairwise. It's 3 people, 4 people, right? Okay. Technically, you can represent that explicitly using concept of hypergraph. But let me tell you that within the context of data analytics and most of the analysis, you don't need to go to hypergraph. Because after all, if you talk about 3 people sharing a project, you can just have 3 lines connecting all of them, right? Does that make sense? Does that make sense, right? Okay. Think of it as, you know, you can call someone. You can always reach someone within that group by knowing one person and then link the rest, right? So we are just going to stick with this definition called edge, which only has I and J. It's not I, J, and K. Okay, it's always I, J. Therefore, if you look back at maybe class number 2, what kind of mathematical object is going to be the natural representation of this? If V1 to V10 can be represented as a vector, what about list of connectivities between I and J? What do you think is going to be the mathematical object? Matrix, right? Right? Because matrix naturally has 2 indices. Does that make sense? Okay, so now I want to imagine everything in your head, okay? But you see it a lot easier, okay? So this is, so when you read the graph versus network, so when you go out in the real world, you will see the word network a lot more than you see the word graph. Okay, does that make sense? Social network, they don't call it social graph. But from analytical perspective, we call it a graph. Okay, but the thing that the problem you work on, chances are has the word network in it. For example, I'm working with Department of Pharmacology, their bioinformatics, biochemistry, or research section, we're looking at metabolic pathway. Metabolic pathway links metabolites of this type with that type. The word they use is metabolic network. But when you want to analyze it, it is a graph. Okay, so network is kind of like an application or real world things. Okay, social network is a real thing in life, right? But if you want to represent social network mathematically, you use graph. Okay, but graph is kind of like still abstract. So sometimes you want to keep it as, in a way, instead of drawing a graph like a circle and lines, you want to keep it in an Excel format. How would you do it? Well, you translate graph into matrix. Okay, because it also has IJ, right? Okay. So these three things are always kind of like correspondence. Okay, the real thing you want to know about is network. That's real life. That thing, in terms of mathematical relationship, it is a graph. But if you want to store the relationship number IJ, well, it's much nicer to store it as a matrix, right? I'll give you a special word for it, for this kind of matrix. The matrix that corresponds to graph is called adjacency matrix, but we'll come to that. Don't worry about it. Okay. So this is the concept of, now, do this with me because this is your homework as well. Example data, okay, example data, network graph. Now, you don't have to work, again, in your project, you're not forced to use network example data. You might as well, okay? But, so example, now, there are obviously 228 of them. Okay, so for example, what are they? Okay, so first time you click Shift Enter, it's going to take you along, well, a little bit because it has to go to the internet. So there it is. These are all the network data. These are all the network data. You will notice, can you see the screen? Okay, so there are 228 of them. Okay, this one is American college football. So I would imagine this is similar to the British Premier League data that I was working with in 2004. Okay, but this is probably more recent. Okay, now, so these are sport, you know, blah, blah, blah. But then you come down here, you start to see things like metabolic network. There it is, right? So see that I mentioned to you before? The things that I want to work on is metabolic network. That's what happens inside your body. Okay, that's how your body uses energy to do things. Okay, in this case, it happened to be a metabolic network of some bacteria of whatever. Okay, so these are kind of like example. Well, let's just take one randomly. We don't have to. Okay, you can take one randomly. Now, I want you to take a minute, glance down this and see which one you think you like to work with. So let's say for some reason I'm interested in, yeah, let's go to some kind of bacteria. I think this is E. coli, right? This is a thing that makes you go bad. Okay, so my graph data equal to, let's say, example data, and I don't know if I need the double bracket or not. Let's try. Okay, there it is. Now that's a little bit mean. Okay, so apparently, you can think of this little thing, each individual nodes. Now that's a little bit. Hey, let's look at this one. This one is a little bit nicer. Okay, there you go. Let's look at this guy. Okay, let's look at this guy. Okay, now my question is, can you see this? Now, forget everybody else. That's too complicated. Just look at this guy, very tiny, okay? So there are altogether 5 metabolites, 5 chemical that have reaction or enzyme. I don't know what this is, okay? I'm not a biologist. Let's say there are 5 protein, 5 enzyme, 5 metabolites that have relationship with one another in the sense that, you know, one begets another or whatever, okay? Okay? So what's N? N meaning the size of V. It's V1, 2, you can arbitrarily say this is 1, 2, 3, 4, 5, right? Does that make sense? 1, 2, 3, 4, 5. Again, how many possible lines are there? 25, right? 25, I to J. However, in this case, you will notice that the line has no directionality. Okay, the line has no directionality. In which case, what it means is that IJ and JI is the same relationship. Okay, so let me give you an example. Let's say you two right here are brothers. Okay, let's say you're the older brother, you're the younger brother. Okay, so if I want the relationship to say is an older brother of, where would the line point from and to? It would point from the older brother to the younger brother. Okay, so you can think of it as an arrow. It's a direction, right? Can you point that arrow from the younger brother to the older brother? No, doesn't work, right? However, if I change the relationship to is a sibling or is a brother, not older, not younger, just ordinary brother, is a brother of, then in this case, there are actually 2 arrows, right? You are the brother of him, he is a brother of you. Okay, so there are 2 arrows. One point this way, one point that way. Now, in situation where the relationship always bidirectional, okay, like is a brother of, in that situation, instead of drawing 2 arrows which head point from left to right, right to left, they'll just draw 1 line with no arrow, with no arrowhead, and that's what this is. Okay, so in that case, the relationship is mathematically it's called symmetric. Okay, A is a brother of B, B is a brother of A, right? But if you say A is an older brother of B, you can't say B is also older brother of A. It's not symmetric. So relationship right away get to the idea of, yes, you can have altogether n square relationship, of which n of them is a relationship with oneself. But if that relationship is directionless, symmetric, then you cut down the number of possible relationship to half, right? Because I don't care if you say A is a brother of B, it's the same thing as saying B is a brother of A, because one implies the other. Okay. Now, in social network, obviously this matters, right? Think about it. In a friend network like Facebook, the relationship, let me ask you this, relationship friend on a Facebook, does that one have arrowhead? Let's say A is a friend, A and B are friends on Facebook. If I want to refer to their relationship, is it symmetric or asymmetric? On Facebook, it is symmetric. Yes, it is symmetric. However, technically, before they were friends, one of them has to invite, right? So technically, you can say that, you know, one is an inviter of the other one. So you can draw an arrow direction. But because right now, when you go to Facebook, that information is no longer available, right? So you have no idea. You know that these people are friends on Facebook. You can't say who asked whom, right? It's like you see a married couple. You can't say who asked whom out for a date. All you know is that they're married at the same time. The minute the husband is married to a wife, the wife is married to a husband. Okay? So that marriage is directionless. It's symmetric. Okay. Right. So this is one example. I don't know. Okay. So let's go back to our notebook. Now, I happen to, okay, so these are all the Zachary quadratic graph. Okay. Now, you can do exactly as the book say, which I think I suggest you do that at home, or you can do it here. Okay. But I'm going to ask each of you, okay, to play with at least 2 examples that are not in here. Okay. So I happen to say that there are these examples. Okay. Now, why do I do this? My example network consists of 1, 2, 3, 4, 5, 6 network. Okay. Don't have to take pictures in the book. Okay. So dolphin social network. Okay. By the way, there is such a thing as a dolphin social network. Dolphins are not fish. Fish, they're very generic. They don't develop relationship between, except during spawning time. But dolphins are very social. Okay. If they're not friendly to one another, they don't swim together. So they are buddies. Okay. There is a social network, like, I swim with you, you swim with me, that sort of deal. The other one is called Eurovision votes. I just happen to pick something that looks interesting. This would be, I don't know if you know what Eurovision is. It's a song contest, right? And in Europe, once a year, it's a big thing. Every country come and sing. And it's very extravagant. And the country can vote for any country. I think you can't vote for yourself, obviously. Otherwise, every year it'd be boring. So every country has to vote for another country, I think. I think that's the rule of the game. Okay, so this is a record. So maybe Finland votes for Austria 3 times or something like that, whereas Austria vote for Finland once or something. Okay, so this will make sense. Okay, so right away you know that this is directional. It has an arrow. Okay, votes. Okay, let me say this is interesting. This is actually musical. And the relationship is defined as appear on stage together. You can think, yeah, in a play, right? Some characters are always together, but some characters are like from different part of the story. Okay. What else? Simple food web. Now, I'll tell simple food web. Obviously, if you have the word food. Okay, animals that you are basically part of a food chain, right? Is this relationship symmetric? Well, probably not, right? Right, because lion would eat a dog, and a dog would eat a small cat or something like that. Okay, it usually doesn't go the other way around. A cat doesn't eat a dog doesn't eat a lion or something. Okay. World Cup. Okay, this is also like who beats whom. But the difference between World Cup 1988 and the data that I showed you earlier is in football league, you have more than 1 match, right? So Liverpool and Arsenal meet more than once. Whereas in World Cup, it's kind of like a competition, like a tree. So you can only play like once, I think. Okay. Sometimes you don't meet at all. Zachary quadratic cup. I don't know why. I think this is very popular example in some books, so I just brought it in. Now, I happen to use name this food web as example network 0 because this is the one I'm going to use a lot. So, oops, sorry. Okay. Now, right. So now that's the data. Now, technically speaking, I haven't got a graph yet, right? Because the reason I can only make a graph if I did this. So example graph, right? Oops, sorry. example graph, network graph, sorry, example data, network graph. So example graph, and then this guy. Okay, so now all I've got is just names, basically. I just look up names. Okay. So what I need to do is to actually put this inside here, right? So I just make a simple loop. That's all. It's an association thread. Okay. So you guys know what this does? Okay. It's the name pointing to the graph data and applies to all the name. Okay, let me say this. Okay, so if I say this, if I say this thing, okay. Okay, can you guys see this? Oops, sorry. I want to make it the font smaller. Oops, too small. Oops. Okay. So let's say I've got this guy, right? Pointing to this guy. And I also want World Wide Web. World Wide Web. World Wide Web to point to example data, open bracket, okay, right? So basically, I want the name to point to the example, comma. I want the name to point to the example. Did you guys see this? Let's make a smaller one. Sorry, let's make it this one. Okay. Okay. Right. And I want this to be an association. So I did this, right? Association, you remember in the second week, sorry, not the third week. Okay. So say my, okay. See that? So this name point to this graph, this name point to that graph. Now, I don't want to do this manually. So how would I do it? Anybody? Okay, nod your head if you understand what this means. It's an association of name to the data set by that name. Name data set. Now, if I did this 100 times, I'm going to be tired, right? So what I want to do is I just put this, okay, comma, Wikivote, comma, as a list, right? Right? Okay. Okay. And I just make this association thread of it. I take this form and I put it here. Now I call this a variable. This is called, that's it. Okay. And I make this a function, right? Okay. The function. And then I apply to this. That's all. Okay. Oops. Oh. Okay. So, sorry. You can do this many way. What I did was actually this. I just basically I did this first. Example, and then I apply this. Okay, so I did this first. Okay, example data. Okay, bracket apply. So I did this. Oops. First. Okay, and then I use this name and then association thread. Okay, same thing. Okay. So that's it. So basically, so now I can call, so when I did this, my example graph, it becomes, so let me do this separately. Oops. Okay. Okay. So you will see that this example graph looks like this, basically. Okay. So if I say I want to look at Eurovision vote, I just put down Eurovision votes. Okay. Now remember, association or dictionary in Python is one of the most useful thing. So if I want to look at something else, like what else do I have? Simple food web. Okay, I get this. Okay. Yeah, simple food web is a nice example. Actually, I don't know why I still start with that. Okay. Can you guys see what's going on here? Simple food web has how many entities? Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 animals or vegetable. Okay. And the arrow, what does the arrow say? By the way, this is the sort of thing I would ask, for example, on the exam. I ask you to say, what does the arrow represent? In English. Come on. I told you that it's a food web. So the arrow say, I am eaten by. This bird is eaten by this bird. This rat is eaten by that rat. Okay. Now, in some ecosystem, things are more complicated because a crocodile can eat a bird, but a bird can also eat a baby crocodile. Okay. So sometimes the arrow goes both ways. In this example, life is very simple. Okay. Sunflower gets eaten by all kinds of bugs. Okay. This bug gets eaten by that bug. These bugs don't eat each other. This bug gets eaten by a bird. This bug gets eaten by another bug. Only this bug, right? So this is a very kind of good example. Okay. Okay. So once again, how many entities are we talking about? 12. Do I care about the attribute? Like, what color is it? In this case, there's a picture. Okay. So you can ask, yeah, it's yellow. This is red. But from my perspective, I don't care. Right? I don't care. The only thing I care is the information that has 2 indices. In this case, the first index is I, second index is J, and the relationship is I is eaten by J, or I is a food of J. Okay. Now, if I define the relationship as who eats whom, then the arrow would obviously point the other way. Okay. You know why they draw it this way? Because biologists are more interested in how nutrient travels up the food chain. Okay. So if you think about it, even though the bird eats the bug, actually the direction of travel is from the bug to the bird, because that's how nutrition goes, right? Okay. So they don't think of it as sort of like who's bigger than whom. It's more like whose nutrient goes up to whom. Okay. So this is why. There it is. Now, thing is, I do the same thing, except I also want the name of the vertex. So in other words, if I did this like before, this one happens to have a picture, but if I did say what is called Eurovision votes. Okay, you can see that this is kind of like nameless. Okay, so you can't tell who is whom, right? Now for this data set, because it's kind of an example, so they give you something like a vertex list, I think. Vertex list of this guy. Okay, so that gives you the country. That gives you the country. Now, so this thing here is not only do I have the labels. Okay, so now I want to plot the graph. Actually, by using the graph name, I'm already plotting it. Okay, so in fact, it's kind of redundant to say graph plot. Yeah, it's kind of redundant, right? It gets the same. Actually, this is the full version. This is an object. This is a graph plot. But for shorthand, if you just write the object itself, you also get the graph automatically. Okay, it's like number 7. It always shows. Now the difference is, of course, if you use graph plot, then you can start doing something like formatting. Okay, something like image size, large, tiny. Okay, obviously, right? So whereas this just has one standard. So graph plot allows you to do all kinds of stuff. So this is the reference page. Go to that, check that. You can also have 3D. Okay, let's say 3D. Take the 3D graph. So this is now this one is not that interesting because there's no hierarchical structure, so it's kind of a flat thing. So read this graph plot. Now, I make this function table from the header. You guys remember that, the function table? Okay, so otherwise, so do this at home. So I just make the summary. So I want to look at, this is the graph plot. This is a vertex list. And this is an edge list. Now, you'll see that this is actually the most intuitive way of looking at things, right? But imagine that you have like a really huge thing, right? Just like this example I had earlier, something like this thing. Okay. Okay, it's so you can't tell what's going on, right? So even though it looks nice for a small graph, when you work for a real thing, real life, like Facebook, social network, you can't really use graph plot always, right? So if you have a plot of who knows whom in this class, you can put a picture of every one of you, right? But for a Facebook friend, that's too much. So you would do things like vertex list, so list of the vertex, edge list. Now this would actually say, okay, the individual. So look at how many lines there are. There are 12 items here, right? 12 items here. 12 items here. And how many lines are here? Well, as many arrows as there are arrows. So you can verify that there's an arrow going from sunflower to this guy. Okay. So there's a sunflower to Laos. There's a sunflower to caterpillar. There's a sunflower to caterpillar to grasshopper. Where's grasshopper? There's a grasshopper. And there's also going to be a grasshopper to, I think this guy's a bat. Grasshopper to Tawi. I guess that's a kind of bat, I think. I'm not sure. Ladybird, go to a bird. So ladybird, ladybug, go to, oh, Tawi is a bird. Sorry, it's this guy. This guy's a bird. So Tawi is a bird. Tawi or Tawi. And Tawi is also eaten by an owl. Tawi is eaten by an owl. Okay. Tawi is also eaten by mosquito. Oh, really? Mosquito eats that? Where's the mosquito? Oh, there it is. Ah, okay. Yeah, that's one example where they eat each other, right? Well, technically, it's not eating because the mosquito is not eating the whole bird, but the mosquito feed off the bird. So the bird is a food for for mosquito. But you know, if you're not careful, the bird turns around and eat the mosquito. So yeah, so you can have two directions. This is the only case here, I think, where you have two ways. Yeah. Okay. Right. So what can you say about relationship? It's very messy, right? It's messy. It's not like in a military organization or organization chart, right? Where a private salutes a corporal, corporal salute the sergeant, sergeant salute the major, and all that, right? You keep going that. This you can have relationship going backward. So it's very messy. Now, so still very intuitive, right? Now, think about it. What matters about graph? What matters about graph? This picture, what does it matter? Can I put this thing? Okay. Now this thing is eaten by this thing. Watch. Look at my hand. The ladybird is eaten by a tawi. A tawi is eaten by an owl, right? However, can I also draw this picture, but I put the ladybird on top of an owl, like higher than owl? Yes, I can. As long as the arrow moves with me, it doesn't matter, right? So there's no rhyme or reason why anybody is other than the fact that, you know, you have to spread the picture out. Okay. So think of this thing first. Think of, wouldn't it be nice to have a way of spreading out the nodes so that you can clearly see the picture? So that's what graph layout is all about. Okay. Graph layout. Okay. So read the concept first, right? So I can do this. Let me just do this right away. So again, let's go to graph plot. Go to graph plot. Graph plot. Okay. Now type. I want you to type with me. And example data. Oops, example graph. I think. What was it before? I used the word example graph. Yeah. Example graph, and I use something like food web. What's it called? Food web. Food web. Food web. Simple food web. Okay. Now, if you haven't created the example graph, you can just use example graph. And then, oh, sorry, example data, graph, data, and simple food web. It's the same thing, right? Oops. Example graph, not graph data, network graph, sorry. Okay. Oops. Okay. Oh, forgot the bracket. Okay, so that's this thing. Okay, now the same thing. Okay, now this is a default picture, right? So obviously you can do something like image size tiny. Yeah, so that's gonna be small. Okay, fine. You don't want. Okay. Now the interesting thing is that one of the option has to do with exactly how do you do the graph layout. So this is called graph layout. Point two. Now you're gonna get a lot of suggestion. So let's go to layer embedding. Okay. Okay. In fact, this hasn't changed because by default, maybe for this case, it was layered embedding. Let's say spring embedding. Circular embedding. Oops. How come? How come? How come? How come? How come it's not changing? Ooh. It should change. Okay, let me come back to that. Okay. Well, the idea here is that you have this thing which represent reality, but that reality doesn't have a location to it, right? Because you just happen to put an owl here, you put a bird here, but in reality, the bird is whatever, okay? So the location doesn't matter in this layout. So alternatively, I can put this. I don't know why it doesn't work. Sorry. Great. I want to show you that there's some many. Maybe maybe there's something about this simple food web that doesn't allow. Hold on. So let's do this. Let's graph layout. Or maybe because it's an example graph. Okay. Okay, well, okay, we'll have another, sorry, my apology. We'll have an example where you can play around with the graph. I think the example graph, maybe it doesn't allow different layout. Anyway, okay. So let me ask you this. Okay, do you see this? This one, the location of the bird and the owl is meaningless, right? Right? I can put the bird over here. As long as the arrow points in the right direction, it's okay, right? Does that make sense? Okay, not your head if you see. Okay, so the location of the actual node, okay, the actual vertex doesn't matter as long as you keep the arrow pointing from I to J correctly, right? Okay, that is true. However, let me ask you this question. Let me ask you this question. If this were to represent a real space, okay, a real space, would you probably have the notion that, yeah, it doesn't matter where individual animals are, But would you agree with me that chances are, let's say there's a flood happen, okay? Catastrophic flood happens, everybody dies. Chances are you will probably find skeleton of birds and owl closer together than you would sunflower, right? Can you imagine that situation, right? Because they have this relationship of one eating another. So maybe there is something like a geographical distribution. So maybe even though the location doesn't really matter, okay? You can imagine that maybe it matters a little bit. Okay, maybe it matters a little bit. Maybe there is a notion of, hey, these guys should be close together, but further away from that guy. Does that make sense? Does that make sense? Now, with that in mind, think of last week where the actual distance defined cluster, right? So you can imagine that even though the location doesn't matter, it would probably make sense if that location has some kind of approximation information. In other words, I just told you that I can put ladybug over here, right? But at the end of the day, it's probably the best that it belongs here, right? It makes best sense, right? That it's close to where the food source is. Now, I can put the ladybug way over here. The graph will be correct. Okay, but the arrow will be really long, right? It's not nasty. So you can think of the mixed notion that, yeah, the actual physical location doesn't matter. But in an abstract space, hey, location does matter. That is the concept of embedding. And this relates to the concept where words are similar. That's why you have things like cats and dogs are close to each other in that embedding space. Okay, I'll come back to this. Okay, meanwhile, I just want to work with it. So, yeah, let's do this. Make an example. So, now, just type exactly like this. Okay, undirected edge A to A, undirected edge A to B, undirected edge B to C, undirected edge C to B. Okay, I'll give you a minute to type. Okay, and you're gonna get exactly this. So this is undirected A to A. You get this. Now, if I wrote down, let's make it cat to dog, cat to dog. Okay, I get this, right? What if I do this? Directed edge, cat to dog. You notice that there's a difference, right? There's an arrow there. Okay. In other words, if you go back here, if you go back to look at this thing that I drew earlier, this is the graph. And I list the edge. I use this function called edge list, vertex list and edge list. So I have a graph. I list the vertex. I list the edge. Conversely, I can start with the edge. I don't know if this thing works. Okay. I can start with the edge, comma. Oops. Hold on. This one is in a table. Okay. So I can start with the edges. Sunflower point to aphid. Sunflower. Okay. And I can call this a graph. Bum, 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 bum. You don't need this. You don't need the inner bracket. So. Okay. Now let's say I did this. Okay. See? This is actually, so I didn't bring the whole graph. I just brought some of it. So obviously you will see that sunflower go to aphid. So this is sunflower, go to aphid, go to grasshopper, blah, blah, blah. And then, okay. So this is basically this guy. 1, 2, 3, 4, right? Okay. So the point is the example graph basically came from this. Okay. This is how you construct. Okay. So in the example, the graph came first. In the example, the graph came first. Then I used the function called edge list to list the edges, right? But when you construct, you actually start from the list of edges. So that's why in your data, now as a data, you can do this now. So let's say, okay, you can make an example of your own. So that is mom. Okay. Say something like dad loves mom. Who loves whom? Okay. So let's say dad loves mom. Directed edges. Okay. Okay. So, and mom also loves dad. So let's mom also loves dad. And we can have something like dad, mom loves you. And then, comma, directed edges, dad also loves you. Now, for some reason, you don't love your dad. Well, let's say you don't love your dad or your mom. What does this graph look like? Okay. So that's the list of edges. So I make it a graph. Okay. Dad loves mom, mom loves dad. Dad loves you, mom loves you. Okay. So let's make it the image size small. Okay. Now this one obviously doesn't have a label. So let's add it something like vertex label. Vertex label. Now this one, because you have it in the database, you just say automatic. Okay. So there, right? So you can imagine that this is your data. And in fact, when you work with what's called graph database, that's the information that's stored. Okay. See that? Directed edge from dad to mom, mom to dad, mom to you, dad to you. And maybe add another one. You love dog. You love the dog. Okay. Okay. So there it is. Right? There it is. Now, so far, this is just data, right? So you can imagine that if you see this, if you have this, this is your information. Okay. However, in real life, maybe you don't have this. Imagine what would you have? Guys, what would you have? Maybe you have a spreadsheet, right? That has dad, mom, dad, you, dog, right? So in other words, you can convert from table to graph. Okay, and that's probably some of the more usual way. So if I work in, say, biology, metabolic graph, people work with graph all the time. Okay, People work with graph all the time. So when I go to that database, they would actually give you something like this, like a graph object. But if you work in something like that, you know, phone number or student ID, something that comes in a table, you have to create the graph yourself from table. Okay. So in other words, you would take the first one from the first column and the second one from the second column, create an arrow between one or the other. Does that make sense? Right? Okay. Now, an easy way to do is obviously to use this thing called directed, okay, association. Anyway, so playing with graph, I gave you a lot of links here about how to play with directed edge, undirected edge. Okay. Now, so what if I can quantify this? Okay. Relationship is not a yes, no all the time, right? Because your dad can love your mom more than your mom loves your dad, or let's say. Okay. Let's say how much one loves another goes from scale from 0 to 100. Okay. Then maybe the amount dad loves mom and mom loves dad are not the same. Maybe mom loves dad more than dad loves mom, or you love mom more than mom loves you, or whatever. Doesn't matter, right? What are those called? Those are called weighted relationship. This would be right here. So if you actually add a number to it, okay, you can add a number to this directed edge or undirected edge, and it will give you a number associated with it. Okay. Now, normally you can use a thickness. Sometimes you can draw it with a thickness. So this would be that. Okay. Okay. So far, we've been talking about one relationship. One relationship is called monoplex, one channel. If I have more than one relationship, it's called multiplex. So it's actually different kind of edge. Same set of vertex. Maybe this is a vertex. This E1 defines relationship of friendship. This EK defines relationship of project sharing. E2 may be relationship of nationality sharing or something like that. Okay. Okay. Now, this is very important. Now, and I'm going to go to a break real quick, and then we'll come back on the screen, and then we'll come back. Okay. So I have this thing. Let's say Excel. Okay. So let's do this. Okay. Who loves whom? Okay. Who loves whom, right? Who loves whom? So let's say dad loves mom. Mom loves dad. Dad and moms love you. And then you love dog. Let's say you love your mom, but let's say you take care of your dog. Okay. So this is one way of storing the graph, right? So how would I do this? How would I turn this into graph? I take this one and that one, I make it directed edge. I take this one, that one, directed edge, right? So that's one way. Okay, that's one way. So that would be storing your graph as edge. So this thing will be called edge list. Okay, this thing is called edge list. Does that make sense? Easy, right? Well, it turns out easy, yes. Powerful, not. What do I mean by powerful, not? Okay. This thing only allows you to create the graph. You cannot really analyze a lot of things about it. There is a better way of representing this graph. So I'm going to representing it with adjacency matrix. Okay. So in this case, I'm going to say that mom, you, dog. Okay. Same information, but this one is actually more powerful. That mom, you, dog. Okay. Now, all I ask is that you put 1 when there's a love. Okay. So does that love mom? Does that love mom? Yes. Does dad love you? Yes. Does mom love dad? Yes. Does mom love you? Yes. Okay. Do you love dad? Apparently you only love dog. And the dog doesn't love anyone. Okay, let's say the dog loves you. Okay. Let's go back to this example. Dog loves you. And let's say the dad loves dog as well. Dad. This is more interesting. Okay. So let's add this information. Dog loves you. And what else? Dad loves dog. Okay. So this is called an edge list. This is an edge list from this to that, from this to that, from this to that, from this to that, from this to that. Okay. It's a very economical. Okay. Let me write. Let me memorize this. I'm going to ask this on the exam. Which one's more economical? Edge list is a very economical way of storing the graph information. Right? It's a very economical way. However, this one is better. And I'll tell you why it's better later. It's called adjacency matrix. Okay. Do you love dog? Does dog love you? What else? Dog. Your dad also loves dog, right? Okay. So notice what happened here. In this case, how many lines do I need? 1, 2, 3, 4, 5, 6. Why do I need 6 lines? Because each line contains an edge, a vertex, right? Here, on the other hand, how many numbers do I have? I actually have 16 numbers, guys. 1, 2, 3, 4, 5, it should be 7. Yeah, 7, okay? So you guys see this? This is how many people are there? How many entities are there? In this case, you have to see what's the common, right? So it's only dad, mom, you, and dog. So 4. Out of these 4, how many lines do you need? As many as required. Okay, there's only 7 lines of love. Okay, dad loves mom, mom loves dad, dad loves you, mom loves you, you love dog, dog loves you, and dad loves dog. Okay, that's it, 7 lines. Now watch this. Here, I list dad, mom, you, and dog. So this is all the edges, all the vertex, and then I put 1 for each love. What this means is that I also put 0 here. Implicitly. So what I'm trying to say is this one is not efficient. It's always n square. Okay. However, for analysis, this is very good because now you have essentially what? a matrix. Okay. So what's cool about this matrix? What's cool about this matrix? What's cool about this matrix is that the relationship may change, but you can have this kind of like 4x4 to represent that month you, right? So every month things can be different. Okay, maybe you stop loving your dog or whatever. Okay, or you can quantify it. Okay, maybe you only love your dog 50%. So it's instead of 0, 1, you can make it a percentage, right? Okay. So what it means is that, okay, what means is that, okay, so right now it's just a yes or no. So basically just this. Okay. What I can do is that this graph my graph G is equal to graph. Okay, let's just make this assignment, this graph. Okay, G is graph. Now, okay, if I type in G, it's this. Okay, if I ask for adjacency matrix out of this graph, I will actually get this. Watch this, okay? Adjacency matrix, it gives you sparse array, meaning sparse array is a way of saying, I don't want to keep the whole matrix. I want to keep the edge. But the whole matrix looks like this, guys. Matrix form. See? 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1. Okay? So that's it. That's a matrix. Okay? So conversely, I can do the things the opposite. Okay? This is my, okay, adjacency matrix equal to this. Okay? And then I say graph, plot, adjacency graph of this. Okay, now we go to the screen. Now we go to the screen. Now we go to the screen. Okay. Okay. Can you guys see this? Okay. So this is the matrix turned into the graph. So okay. Okay. So now you have this thing, and an arrow. Okay. I'm just going to use numbers. I don't want to write mom and dad. 1, 2, and 3. Okay. And let's say 1.23. Okay. 1.23. Yeah, that's the graph. That's a relationship. But once again, this is very hard to visualize if you have 100,000, and this is not how you store it. So how would you store it? You would store it as 1, 2, 1, 3, and then 2, 3. All right? Right? You can store it this way, right? So basically, list of lists. Okay. Right? Okay. This makes sense because this is 1, this is 2, 2, 1, 3, and 3, 3, 2. And in this case, you just point from the left to the right. Okay. However, so this is edgeless. And this is the graph. Okay. Now, instead of doing this, I'm going to propose that you do matrix instead. And I have a 3 by 3. Right? So now it's 1, 2, 3, 1, 2, 3. And everything is 0 except 1, 2. That's the word 1, 1, 3. And 2, 3. Sorry. Yeah, 2, 3. 1, 1, 2, 1, 3, and 2, 3. Everything else is 0. This thing is called adjacency matrix. So this matrix requires you to fix a position, right? So if I don't use 1, 2, 3, I use dad, mom, you, and your dog. I have to make an assignment that dad is the first row, mom is the second row, you are the third row, and dog is the fourth row. Okay, then it makes sense. Otherwise, the matrix would just permutate. Okay, so this is the reality. Okay, the reality is dad and mom and you and the love relationship. Okay, that's reality. You represent it as a graph, which is an entity, right? And you don't care about the property about the entity at all. You only care about relationship. So that's a graph. So this is an abstract representation of reality. So this is reality. Now, because you want to do this with data, with huge network, you can't draw this thing the whole time, all the time. So you have to store it as a data. You have two options. You can only keep the list of edge or designate 1, 2, 3, 1, 2, 3, and do this thing. Okay. Now, technically, this is a matrix. Okay. Mathematica, when possible, if it notices that there's a lot of 0, it would automatically try to go to this. But you can go back and forth, right? Right? So, in fact, you can go from here to here, from here to there, from here to here, from here to here. They are all equivalent. Okay? So, think of this as reality. This is abstract representation. This is database efficient. Okay? But you can't really see the picture. Let's put it this way. You can't see the picture. It's kind of like hard to see. This is a database as well, but it's wasteful, but it gives you a picture. Okay, it gives you a picture. First of all, you can stand back and look and say, hey, you know, most of the time it's kind of empty. Okay, it's kind of clustered in the top half. Okay, this is graph data. Now, the point is, we're going to go for a break. When we come back, we're going to do analytics on graph data. When you do analytics on graph data, you always use the matrix representation. Okay. Now, let me give you this, just so you understand. In terms of computation, implementation, Mathematica, when you give it a matrix, if it notices there's a lot of holes, it's going to store it like this, called sparse matrix. In fact, this is how NVIDIA or all kind of stuff do it. Okay. Mathematically, think of it as a matrix, but computationally, it's actually stored like this. It's more efficient in terms of computer storage. Okay, but that's not our point. Okay, our point, when we come back, we're going to go from graph data, graph data to analytics. When we do analytics, it's always thought of as matrix manipulation. Does that make sense? Okay. Now, okay, go to a break for a few minutes. We'll come back. We'll do just that.